This is Mrs. Schroeder's chemistry class, and we're going to talk about phase equilibrium from section 11.4 today. Today we're going to talk about the systems that have multiple phases and figure out what equilibrium is. We're going to talk about vapor pressure between liquids and gases and what that means. We're going to use something called phase diagrams and try to understand what a phase diagram is and learn how to use one. A phase is the region that has the same composition and properties throughout. We've used this before. We've talked about homogeneous and heterogeneous things. They have phases you can see. We're talking about states. We're talking about one state or two states. Liquid water has one phase. It's only a liquid. A two-phase system would be liquid water and ice. And if you look at this picture, you see the ice cubes in here. Well, here's your ice cubes. They have a little bit different structure the way they're set up. So this is your ice. Your liquid water, they can flow past each other, a little tighter packed. So I see two phases, two distinct phases and regions. Equilibrium is when there's no heat added or removed, but particles can be moving between two or more different phases. There's no net change in the amount, but specific particles can be moving back and forth between the phases. And we'll take a look at this little simulation to show you what it means when an individual particle moves back and forth. This is a simulation to show you with liquid bromine and gaseous bromine. So if I look up here, I have my vapor on the top, I have my liquid on the bottom. The rectangle is representing the volume. There's my gas and my liquid. And I watch these particles. They're moving. Individual particles are moving from the gas to the liquid, but overall I still have about the same amount, 2 or 3 molecules in the top and then more in the liquid. But they're moving back and forth. This one may turn into a liquid, this one may become a gas. That's what equilibrium means. Vapor pressure is a term we've talked about in the past. We know the pressure of a gas. We talked about with our gas phases and our gas laws. Pressure is caused by the collision of particles on a container. We call that the vapor pressure of the gas. Vapor pressure does change. If you increase the vapor pressure or you increase the temperature, those particles are moving faster. If they move faster, they strike with the particles strike the container more frequently. More frequent collisions means the vapor pressure will increase. And I have a chart that's going to show you this. This is the vapor pressure of different substances at different temperatures. Let's look first at water. What happens with water when we're down at room temperature? There's a vapor pressure somewhere over here. It's pretty low. There's not a lot of vapor at that room temperature. As I begin to increase, I'm beginning to follow this curve. And my vapor pressure is increasing and increasing until it reaches a point of normal pressure at which it's going to begin to boil. If the pressure over top of that water is in fact 1 atmosphere, it will begin to boil at that temperature. That's what's called the boiling point. If I had this in a closed container, I would see the pressure continue to rise of the vapor. But again, if it's open at atmosphere, it's going to begin boiling at that pressure. Ethanol has a lower vapor pressure and a lower boiling point. Ether has an even lower vapor pressure and lower boiling point. Intermolecular forces, water has our hydrogen bonding, so they're holding on together pretty tightly. Ethanol is also going to have some hydrogen bonding, but ether only has dipole. So they're not held as tightly, which means they can be released easier, which means they have a higher vapor pressure at any given temperature, which means that they're going to have a lower boiling point. A phase diagram looks like this. Kind of confusing when you first see it. You're going to see all these different shades, all these different lines. What do they all mean? Well, there's three main lines we're concerned about. The first line is the liquid-gas equilibrium line. And this is when I look and see where the liquid is and where the vapor is. Liquid is here, vapor's here, solid's over here. So anything below this line is a vapor. Anything above that line is a liquid. The next one is our liquid solid equilibrium. And this line, solid liquid, is where the solid and the liquid meet. So again, anything on this side of it would be a liquid, on this side would be a solid. The third line we're concerned about is the solid and gas. This is where sublimation occurs. And this is our line down here. Solid on this side, gas on this side. Now where these three lines meet, you'll notice this triple point. Okay, this is where all three lines meet. At that point and that point alone, you could have all three states at equilibrium. Now it's not to say I can't have three states. Maybe I have boiling water and I throw an ice cube into it. I've got three states at that time. It's not at equilibrium because it's too hot and the ice will melt immediately. But at this triple point, they're all going to exist at the same time. Phase diagrams also have this region called the critical point. And above this temperature, I'm going to have what's called a supercritical fluid. Supercritical fluid is something at very high temperatures, very high pressure, and supercritical fluids have properties somewhat like liquids, somewhat like vapors, but very unique properties. It can be used for a lot of new technology, and decaffeinating coffee is one use of supercritical fluids. They can use things, instead of using water, they use carbon dioxide in a supercritical fluid. And I'll let you guys look into that a little more, but it's a very interesting phase that you can get to when you have a high enough temperature and pressure. You can use our phase diagram if you're given a point and somebody asks you, what is the state of this? If I gave you a temperature of 150 degrees and a pressure of 200 degrees or 200 kilopascals, and I ask you to figure out what phase am I in. Well, if you notice these scales, this temperature, it's not really to scale. They're very goofy in terms of the scale of these things. If you look at the difference between here and here, not really a good scale, but you can kind of eyeball this thing. So at 150 maybe, somewhere around there, and 200 kilopascals, somewhere around there. Okay, if I look at that, this material is going to be, maybe right there, it's going to be a vapor. Okay, at that particular temperature and pressure. So I can use phase diagrams to figure out what kind of state I have. We're going to learn how to do this in class tomorrow. We're going to practice, let you guys have a chance to see if we can build a phase diagram. This one's going to be for carbon dioxide. One difference is we look at water. Water is the only unique substance in which the solid will float on top of the liquid, meaning the solid is less dense. Because it's less dense, when I increase the pressure, increasing the pressure is going to force it to the more dense material. So increasing the pressure forces it over to liquid. Most other materials will be the other direction, where the line would look this way. But we'll cover that tomorrow in class. For now, just make sure you have looked at the phase diagrams. Look at this different vocabulary we're learning in this class: triple point, critical point, phases, and be comfortable at being able to use these in class.